This is Star Talk. Neil deGrasse Tyson here, your personal astrophysicist. We're going to do cosmic queries today. Everything black holes and space-time. And I got with me my guest co-host, Matt Kirshen. Matt, welcome back, dude.
Thank you. I'm joining you from my family's spare bedroom in London right now.
Oh, you mean your parents' basement where you live? Just say
That's exactly it, yeah. I commute to LA every day from the basement where all my toys and games are.
I knew you were full geek, but the whole story, you're still in your parents' basement. You can confess that.
Why not?
You're in safe grounds here to admit that to us.
This is no judgment podcast.
No judgments at all. Good to have you back, and you're the host of Sometimes Science.
It's probably science.
Probably science. Damn. Okay. Probably science, on which I have been a guest in the past.
You have indeed.
I have, and I enjoyed my time there. So, Matt, while I know a little bit about black holes and a little more about space-time, I don't count myself among the world's experts, but we have a friend of Star Talk who is. Of course, that's Janna Levin. Janna, welcome back to Star Talk.
Thanks. I'm glad to be here. Sort of here.
Yeah.
I'm meta here, virtually.
Yeah. Janna, you're like a neighbor up the street from the American Museum of Natural History. You're a professor of physics and astronomy at Barnard College of Columbia. And it's just great to have you, just a friend of what we do and a supporter of all of this.
Yeah, I love being here.
And to lend your expertise. You're not lending it because we're not giving it back. you're giving us your expertise on black holes, cosmology, the space-time continuum, and all that goes with it. So just before we start off, I just want to alert people that in your spare time, you actually are one of the founders of a marvelously conceived project, Pioneer Works, over in Brooklyn, across the river. You merge art and science in highly creative and imaginative ways. I just want to congratulate you on
thanks, Neil.
going there. And you've been at it for like years now, right?
Yeah, I really appreciate that. Yeah, we have a live programming where we feature scientists in conversation. You've been over. We've had parties with you, Neil.
Yeah,
and,
but you haven't put me on the stage. I was just there to like
I'm waiting
people,
for the right time.
Oh, okay.
I have also been there and not on the stage. They didn't want my expertise, but I went to
Matt, you and I don't cut it. We're good enough for the audience, but not to actually do it.
I mean, I think I'll get there eventually, but I'm not so sure about you, Neil. I've got some deep expertise to share.
I'm happy to put you both to work. Be careful what you wish for. So the big project there has been lately Pioneer Works broadcast since the pandemic, which is our virtual manifestation. It's Pioneer Works Beyond the Walls, where we cover art, science, music, tech, kind of multimedia extravaganza.
Excellent. So now you can reach a far greater audience than who shows up in Brooklyn. So Matt, you collected questions from our Patreon members. They have exclusive access to our Cosmic Queries format, and everyone else gets to hear their questions. And so what do you have lined up for us? This is like a grab bag. It's a grab bag of black holes and stuff, right?
Yeah, there's a really nice assortment of questions. I'm going to start off with this one from Matthew Power, my kind of superhero namesake. That's
you're Matt Kirshen, and this is Matthew Power.
It's Matt Power. This
okay.
is Matt from New Jersey, who is also currently reading Black Hole Blues, which is one of Janna's books. I've read that; it's an excellent book, and Matt is also enjoying it. And Matt says, my question is, if there were two black holes orbiting one another and generating powerful gravitational waves, is there a possibility that a small object, he says perhaps a ping pong ball, could actually be carried away by the waves, thus making gravity a repulsive force in this particular case?
Wow, this is like a surfing ping pong ball.
Wow.
I love it.
That's...
I
what
love
do you think, Neil?
Oh, I love the idea. So, because probably he's thinking deeply, because if you're surfing on a wave in the ocean, the water isn't actually moving. It's just going up and down, and you're somehow exploiting this fact. Isn't that right?
Moving with it. Yeah. I think it's a subtle question. I've wondered about this, but I haven't ever really worked it out. I'm sure somebody might off the cuff know the answer, but definitely what you're doing in space-time, if you're near those two black holes, is you're falling freely. We literally call it free fall. So you're falling freely on the natural curves in the space. So if those curves are changing, that's certainly going to change your fall. For instance, the Earth is falling around the sun, on a curve, on a circle. And if the sun were to disappear tomorrow, the gravitational waves would radiate out, taking the time it takes until it reaches us, and then we'd go in a straight line as though the sun was gone, right? So in some sense, we are definitely moving with those waves. But thinking of it as like surfing, it's cool. I don't know.
Right. If we're not so heavy as the Earth, let's say, or something as responsive as a ping pong ball,
Yeah.
wouldn't the expanding gravitational wave from the disappeared sun or from the collapsed black hole, will that have any effect on us at all to push us? How can a wave move out, but we can't now move with it?
Yeah, I mean, the gravitational energy in the wave can be quite powerful, right? The collision of the two black holes was the most powerful event human beings have detected since the detection of the Big Bang, right? And all of it came out in the gravitational waves. But actually, I think their effect is really quite weak in the sense you would feel the squeezing and the stretching as you kind of bobbed around on the wave, but I don't think it would have enough power to actually carry you along. But we also do know, I think the question was also about repulsive gravitational forces, and actually we do know that gravity can be repulsive. So for instance, the dark energy in the universe creates a repulsive effect on the expansion. So the universe is expanding. Things are getting farther apart because of the dark energy, and that's happening at an accelerated rate.
Yeah, but you're calling that gravity, and are we allowed to do that yet?
What do you mean? In what sense?
You say, well, there's this dark energy, and it's actually the opposite of gravity. So are you legitimately calling it negative gravity?
No, I'm not calling it negative gravity. I'm saying that when we think about curved spacetime, that coming together is not the only possibility, although that is with Newton's laws. In general relativity, when I think of dark energy as a particular source for the way it deforms spacetime, we see a very clear example where its effect on spacetime is expansive. And
wait, I got a good answer.
Attractive.
I got another good answer. Can I raise my hand? You pick on me?
Yeah.
Janna, I'm raising my hand in the front row.
You're the boss. You're the boss.
Okay.
Neil.
Yeah, thank you, Janna. So, just thinking about this more holistically, the very expansion of the universe is carrying galaxies in the fabric of the expanding space-time. So, in a way, we are moving, in a sense, not through space, but with space. And space is carrying us. And no, it's not a gravitational wave, but it's I'll take it as something, it's sort of surfing, even if it's not.
Yeah, that's excellent. The dark energy is just a particular example of that, causing the expansion in an accelerated way, but lots of things cause the universe to expand. Like the fact that it's full of light and energy in all directions causes the universe to expand. And I think you really hit it on the head, Neil. We are moving with the expansion of the space. We are not moving with respect to our local area, right? So that is like the surfer riding the wave.
Yeah, cool.
And then we just get further and further away from each other. Eventually, we won't even see the other galaxies.
I got for a question that is very theoretical to one that I know you have a good answer to, because I know this is something you've both been asked before. Alexander Newhouse wants to know, what is the universe expanding into?
Yeah, Janna. Everybody wants to know that one.
I know you've done this a bunch of times.
No, I just make stuff up, what I've read, but you actually work on these problems. So let's hear it out of the horse's mouth.
Well, let's take it as though the universe was expanding into something, just pretend, then we would be saying, oh, there's some distance the universe has traveled into this other space. But what we mean by the universe is the space. So there's really no logic to thinking of it expanding into something else. The universe is the whole space. There are some relational possibilities that you can think of where the expansion of the universe is like a map of the universe, where we're only reading the legend between things as changing over time. But the map itself doesn't move into anything else. That's one kind of very strange relational way of thinking about it. But no, we do not need to nest the universe into another universe to have it expand.
Okay, I get that. But Okay, so let's up this game a notch.
Yeah.
What conditions what dimensionality, what location, what state of existence must one have to observe the entire expansion of our universe
Well, that's
from the outside?
So there is no way to stand outside the universe.
No, not really, but what?
I think you're trying to disprove the existence of God with me right now. What kind of trouble are you getting into?
I don't think I really mentioned God in that.
Nobody can see and know the entire universe at one time. There's no way of...
Who are you to say that you can't, there is not some platform, some vista outside of everything we know and see that can just simply observe what's going on?
Well, by observe, we mean collect particles and interact. And we do that through paths in space-time. So if you want to literally be in a position where you're gathering light so that you can see the universe and deduce what's happening to it, you're really talking about interacting with something. And that requires that we be in the same universe. Now, I mean, you could fundamentally
You're no
say,
fun. You're no fun. In that.
We could say things that I think are actually
Matt, she could have said, God is out there and he's watching us all, right? Or Santa Claus, he knows when you are bad or good.
And then we sing some hymns and then roll credits.
Right. It is interesting to push this idea and to say, look, these ideas about space being infinite or being finite or expanding, these are just ways of talking. We could also talk differently about the entire universe only as relations, only as interactions. And that's the only thing we understand, that interactions happen over a certain span of space and time. And there's no need to even think about geometry at all or to think about the universe as a space at all. It's just appeals to our intuition. Wow. You're looking at me like, I've had this woman on the show many times.
Okay, Matt, she's crossed over.
I've
crossed over. I don't know that they're bringing her back at this point. Okay.
I mean, and we know that we're often fooled by these interactions. So right now I have the illusion that you're a solid person, that Matt's a solid person, but really you're mostly empty space. These are illusions that we cling on to more easily comprehend the world, but we know that they're not
Matt
true.
Is mostly empty space.
Yeah,
I'm
a lot
solid.
of people say that about me.
I'm solid here.
Neil is solid. There's nothing going on in here.
No, so Jen, you're referring to the fact that atoms are mostly completely empty. Yeah.
Right, and then even if you look at
thought.
fundamentally what the fundamental particles are with atoms, we only understand them in terms of the way in which they interact with things. That's right. The meaning of an electron, is the way it interacts with things. Right, so in some sense, we're just these sort of lists of interactions.
Damn, she got all philosophical on us, Matt.
Well, that's
quickly go to the next question before this gets worse. Okay.
Well, I because you got so philosophical, I'm going to jump onto Scott Allen's question, because Scott from Arlington, who by the way gives the caveat that Scott is stoned right now.
Okay.
I'm putting that right in there, and if Scott is still stoned trying to listen to these answers, I think we're going to put him in some real trouble.
We should do a stoner version of this show.
I'll host it and just get my mate. I mean, that's basically is my podcast. That is probably like we're just winging it.
Star Talk for Stoners. Oh my gosh. We get all the
Scott
topics
wants to know,
best suited for when you're high. Oh my gosh. You know, Janna, we'll bring you back. That's going to be a show. I promise our audience that's going to be a show, okay?
I just fall asleep. It'll be a very boring show.
While you're eating potato chips. Yeah, okay. Okay.
So Scott says, is everything just a form of energy? Is time just a human invention? Combining the two ideas, is what we call life and everything we can observe and understand with our limited senses and minds simply a flow energy constantly changing form? There is no beginning, there is no end, there is no past, there is no future. There is just the present in whatever form of energy we can sense and understand with our mind.
Definitely stoned.
Make of that what you will.
Yeah, okay.
Professional scientists.
Wait, did you just give the answer and you said definitely, and now we can move on to the next question?
I think the answer is yes, and everything's fine right now. And
I just think he's definitely stoned.
That
is such a stoner question.
What confidences do, I'm going to restate the question. Mm-hmm. What confidences do we have Janet, can you and I offer as scientists that there is a physical reality, and just we're not all just perceiving ourselves in the moment, and that what evidences do we have that
I think you made
the
it
universe
worse
has
for me,
meaning
man.
and existence outside of our perceptions?
Yeah, I mean, we're all, I mean, which one of us is the one perceiving? Am I in your mind or solely, or are you
Or are we
solely
both
in
in
my
Matt's
mind?
mind?
Which one of us
Or
is
we
the
both-
genius that
Before Scott
created?
started, before Scott started combining his ideas, there are two questions at the beginning that I don't that are more grounded in, I think, physical or theory. That is everything just a form of energy? And also, is time just a human invention? And I think those two are questions that are potentially
Yeah.
more
I think
answerable.
that well, to deal with the first one, yes, I think matter and everything is a form of energy that interacts
Wait, Janet,
in
you just don't think that.
prescribed
You
ways.
know that. Janet, be careful how you use
Yeah.
the word think.
Yeah.
Okay? Like, you think it might rain tomorrow, but you know matter
Right.
is energy, okay?
Right. It's true. We know that matter
Thank
is
you.
definable essentially. Yeah. And that is interesting. I mean, I think that's also related to this kind of tangent we went on, which is that what does it mean to have atoms in your body? What does it mean to be made up of atoms? Is it means that you have a certain amount of energy and that those particles interact in very prescribed ways. That's what makes an electron different from the positron, is just the prescribed interactions, if not their energies. So, so yeah, that's really all we are. It's beyond that to say what's real is again part of this illusion we have to cope with our perceptions of the world.
We'll take a quick break, and when we come back, we'll pick up the second part of that question, whether time is just some kind of a human construct, with the help of Janna Levin giving us her insights into the universe on Star Talk Cosmic Queries. We're back. Star Talk Cosmic Queries. I got Matt Kirshen as my co-host. Matt, how do we find you on social media?
I'm Matt Kirshen on Twitter. I think Matt_Kirshen on the Instagram I very rarely use.
Okay.
Twitter's the main place I am.
Okay.
And if you don't know the spelling, just kind of get vaguely close and Google will find me.
Yeah, okay. And we'll find you on Twitter then without the underscore, because that's where you mostly post.
That's me.
And Janna, tell me about your social media footprint.
Yeah, I'm more on Twitter at Janna Levin, 2 N's like Anna, and I'm on the Insta, same handle. I sort of treat them a little differently. On Instagram, I kind of post my personal stuffs, my personal business.
Okay, we want to get all up in your
And on
situation
Twitter,
when we go there, okay?
Yeah. You know, yeah, exactly. Not exactly what I had for lunch, but yeah. So, but Twitter, I have pretty serious conversations with people. If they want to ask questions, I'm there. I love answering questions when I'm in the mood, at least,
Very good. All right, so we left off. What's the name of that last questioner, Matt?
So, Scott, we left off his part of the question was, is time just a human invention?
Yeah. There's a quote I remember from Einstein or from his student, John Archibald Wheeler. Was it, time is invented to make motion look simple? Have you heard that?
I have heard it. I feel like it was Wheeler because he said lots of witty things.
Yeah,
I also think it was Wheeler who said time is what keeps everything from happening at once.
All at once? Yeah, okay.
Which is a good one.
And just I got to throw it in here. I first noticed the woman who would become my wife in a class taught by John Archibald Wheeler, the cosmologist physicist.
Oh wow!
Yeah,
no
took the
way!
class
I
together.
didn't know that.
I was sitting in the back row. She was in the front row.
Wow.
So I don't. She probably didn't notice me, but I noticed her. Yeah.
That's adorable.
I can say I noticed her in the space-time continuum on the chalkboard. Okay. Okay. So what do you have to say about his comment about time?
Well, I definitely don't think it's a human construct. Whether time exists in this kind of block time model of the universe where the past exists, the future exists, every bit as much as left and right exist, but we're confined on a particular path through this four-dimensional space where time is the fourth dimension. That wouldn't be just human beings, though. That would be everything would be confined to that space. I presume my cat's death comes before its, after its birth, rather. And, I just presume flowers die after they bloom, and that those are things that are happening to everything in the universe. There are other models that time is sort of not an invention of the mind, but it's like it emerges from very subtle processes, and that in some sense it's not fundamental. But I think that, again, it's a very good thing to talk about. So if we want to meet, we don't just specify a point in space. We have to say a moment in time. And it's very convenient that we all are able to find that moment in time and collect and get together at that moment in time. So that suggests it's not just a figment of our imagination or a human construct.
So maybe I should save this for the Stoner edition, but if you could find a region of the universe where nothing changes, then time cannot possibly have meaning.
Absolutely true. Absolutely. Okay. And in fact, that's kind of a death of the universe model, that the universe everything that can fall into black holes will possibly, if the expansion doesn't dominate, and those black holes will evaporate into random particles, and then the expansion will just make it so that there's only one particle in the entire observable horizon that, and that's disconnected from all the other particles. And so there will be no meaning to time passing. Right. I mean, even for me to experience time passing, there has to be change, which is my thoughts changed, my breath accumulated. There's actual measurable change that I experience as the passage of time. So that is true that we do have internal clocks, but they are very well aligned with our external clocks, making it seem as though there is something external and universal.
Well, while we're talking about external and internal clocks, Jeff Johnson wants to know, why does gravity or high speed cause an entity to move faster through time?
Oh, I see the question. Time dilation is the question. Yeah. Why does time? So,
but first he got it backwards. So gravity slows down time, not speeds it up. So take it up, Janna.
Yeah. So it doesn't actually slow my experience of time. So my experience of time, if I'm standing near a black hole, is exactly like very ordinary. My nicely made watch that I had once synced with my friend back at a safe space station is working perfectly well. It's still matching the number of breaths I take. Time seems to be passing completely normally.
Your heart rate, everything.
My heart rate, everything is absolutely normal. I don't get any benefit out of this dilation. The dilation is only relative to somebody far away. And to somebody far away, I look like I'm moving slowly, like I'm breathing slowly, like I'm aging slowly, like my watch is ticking slowly. So it's only relative to them that it looks odd. But in my experience, it's quite normal. I think the deeper question is, why does this happen? And we can think of both gravity and moving quickly as creating rotations between the space-times of two observers. So if one observer thinks that this is left and another observer is facing them, they understand that they're going to disagree about which way is left. They're not surprised, but they know they can just rotate their systems and then they'll agree, right? So in some sense, as you go closer and closer to the black hole, it's as though you're rotating in space-time. So some of what you were calling space is folding into some of what your friend was calling time. And that leads to time almost as though you're rotating left and to right, almost as though you've rotated time away entirely relative to your other observer. And
wait, so Matt, we should just rename this show Star Talk for Stoners. Okay.
I don't think it's fair that we're not stoned.
It is happening in front of our eyes, Matt.
Yeah. There is a beautifully related question as well on this note from Frederick Johansson from Sweden.
Wait, Matt. I just gotta wrap my head around what Janna just said. So Janna, what you're saying is you use left-right as an interesting analog to this, what you're saying is when you are in the moving faster in the vicinity of a black hole, your time coordinate is, let's use the term rotates in such a way that it's giving of itself to a space coordinate. And
that's right.
So one is losing time relative to the other.
Exactly. And just like you can rotate left all the way into right, at the edge of a black hole in particular, you've basically rotated your time away entirely. And in fact, when you cross the event horizon, what your friend far away thought was a region in space, a center of the black hole, is for you a direction in time. So you've rotated it completely by the time you cross the event horizon, to the point where you think that the dire singularity at the center isn't a point in space at all. It's in your future. And it is as inevitable that you will crush into that singularity as the passage of time is inevitable.
Wow.
So you
And that
can't
was a
dodge
Roger
the
Penrose
singularity in the
result.
center of a black hole.
That was Roger Penrose, wasn't
Yeah,
it? Yeah.
Yeah, actually, I wrote this little article after he won the Nobel Prize for that beautiful work in 1965 for Pioneer Works Broadcast, actually, because we do this series called Picture This, where scientists write about technical articles, like technical drawings. And Roger Penrose has the most wonderful drawing that he drew in this 1965 paper, where he shows basically time starting to move in a spatial direction. He shows that rotation. And he proves that at the event horizon, what's happened is basically time is starting to point inward towards the black hole. It's
So
quite
I love
beautiful.
and I love the left-right starter analogy there. You know what that reminds me? So Matt, you ever heard this joke? It's funny. It says, so someone says, well, two wrongs don't make a right, right? But then you can say, but three rights make a left. Have you ever tried that? Just try it. Make three left turns.
Nice.
You just turned right. It just, if you do the geometry on that, it works out.
Yeah.
All right, cool, Janna. Thanks for that answer. We will totally. We'll have to talk to my producers here, but I think we should rebrand this for stoners, aka for stoners, the stoner edition of Cosmic Queries. Matt, keep them coming.
Well, so Frederick Johansson asks, and this is related because you just talked about the difference of effects of both speed and gravity. Frederick wants to know, if I stand on the equator, my head would age less compared to my feet due to the speed difference. But wouldn't we have the opposite effect due to gravity? Would my feet or head age more in the end? So I believe he's asking that if he's standing on the globe, his head is moving faster than his feet because it's further out, but also his head is further away from the gravitational center of the Earth than his feet. So do these two things both have an effect on the time perception of your head and your feet? And if so, do they cancel each other?
Yeah, who wins?
I would have to actually do the calculation because both are pretty tiny, right? But I can tell you that with like the GPS units, we see the effect of the time dilation when we send signals to satellites and back again, and they have two effects. One is you're deeper in the gravitational potential. So let's say we take the twins, like one astronaut that was in the ISS and the other twin astronaut who stayed on Earth, the Kelly twins. Which one actually was younger? The one who stayed on Earth deeper in the gravitational potential well, or the one who was traveling very quickly in the ISS? And it's actually a known answer, and I forget which one it was. I think the speed of the ISS dominates over being on the Earth in that case. I'm pretty sure.
Okay. However, with GPS satellites, the fact that they're much farther away from Earth than the International Space Station, that they experience much, much less strength of gravity, which speeds up their time relative to us. And so their time that they send us is pre-corrected to accommodate the fact that their clocks tick faster. So, right, Janet, you have to do the math, right? Because there are two competing effects, and to know for sure. But I agree with you. Everything I know about the orbiting astronauts, which are in low Earth orbit rather than middle Earth orbit. Matt, it's not middle Earth like Okay,
Right.
just to be clear.
Right. Orbit.
Not a basement, Neil. I'm
Orbit.
not in a basement.
It's not the Middle Earth. It's Leo, Mio, and Geo, right? Low Earth orbit, Middle Earth orbit, and
Right.
geosynchronous orbit. So they, when you do the math there, the lower gravitational field wins out over what effect their speed has on their timekeeping. So yeah,
Oh, interesting.
yeah, we're good.
Interesting. So thinking about the GPS, we could also think about how if we didn't correct for the time dilation, we would never be able to catch our Uber because it wouldn't be in the right location. And I learned this from Neil recently, that it's actually the rotation of the Earth that's the issue. That if the satellite let's suppose we lost a second, if the correction was never made and the error accumulated up to, let's say, a second, then if you consider how quickly the Earth is rotating and that the grid would be changing, you would find that we could be off by several blocks. So you'd be trying to catch your Uber, in Chinatown, and it would be in Little Italy.
Which is 5
Story
6
of my
blocks
life.
away.
My
These are
Uber's never
adjacent-
where I need it to be.
These are adjacent communities in Lower Manhattan, Little Italy, and
Yes, they're
Chinatown.
adjacent
Right.
neighborhoods.
Yes,
in
yes,
China.
they are.
Yeah.
For those who are not native to the city. All right. Let's take a quick break, and when we come back, more Cosmic Queries, Stoner Edition with Janna Levin. We're talking about black holes, cosmology, and the space-time continuum. We'll be right back. We're back, third and final segment of Cosmic Queries, Black Holes and Space-Time Continuum Edition, which we are dubbing Cosmic Queries Stoner Edition, based on the answers we've been getting and what kind of state of mind we have to be in to even follow them, much less understand them. So, Janna, again, it's always good to have you here. Your last two books, so one of them was The Black Hole Blues, published by, was that Knopf? Alfred Knopf?
Yeah, by Knopf.
Yeah, Black Hole
Yeah.
Blues. Why? I didn't know black holes had emotional states.
Well, the people who were searching for black holes had emotional states.
Oh, okay.
They have the black hole blues.
Oh, I got
They have
you.
the black hole blues.
So this is a story of black holes in our field of astrophysics and the relationship we have
Yes.
to them. Got it. And more recently, you have a book called The Black Hole Survival Guide, which is like a pocketbook, fits right in your coat pocket. And how useful how soon do you think such a book will be useful, where everyone has to have one?
Yeah, they have to have a survival guide. Well, I hope not very soon at all.
Okay.
But we are. Well,
for the sake of the sales of your
book,
book.
supermassive black hole.
For the sales of your
Well,
book.
Let's stoke some worry in the public. Any second now.
It's sort of I have a spoiler alert. It doesn't end well.
Oh, yeah. There you go.
The survival guide doesn't go well.
All right.
It's pretty much many ways to die.
We'll keep a copy of this in our go bag, right? When disaster strikes.
Yeah. So don't you have a book titled Death by Black Hole? I've always wanted to steal that title from you.
Oh, Death by Black Hole. Yeah, I do. It's one. So that title is the title of one chapter in a book that goes a lot of different places. That's right.
Right. It was this collection of essays. if
Yeah,
I
that's
remember.
right. That's right.
Yeah.
On
Yeah.
all manner of things in the universe. That's right.
Yeah. So the survival guide could also be called like Death by Black Hole.
Okay. All right. It's how to not. So it's the non-survival guide. If it's Death by Black Hole.
Yeah.
All right, Matt. What more do you have for us?
Well, I'm gonna turn this to some black hole survival questions because we've got a few and they're great. So from the Czech Republic, Patreon patron Jindrik Prokupek, I hope I've got that close to correct, asks you, I read that black holes are almost 0 Kelvin inside. Why are they so cold and not very hot due to a high pressure caused by enormous gravity forces and lack of heat escape?
I
And
love
is
that
there a
question.
temperature gradient between a black hole center and its event horizon?
And what's 0K anyway, Janna?
Oh, it literally, it just means particles are so cold. They have so little energy that they're just not moving. It's as though, when we experience temperature, what we're really experiencing is the collection of atoms moving at a certain rate and a certain speed on average, and that creates the temperature. And the faster that they're moving, the hotter it feels, and the slower they're moving, the colder they are. And it is true, there's an expression, PV equals NKT, that, you know, in highly pressured situations, the temperature can go up.
Right, that's the thing. The level of physics that I understand. Like, a bicycle pump gets hotter
PV
if you
equals NKT.
and it, if you spray one of those compressed air canisters, they get cold because you're
Yeah.
Janna, I can't believe you wrote it on the chalkboard. Okay.
I love that Janna's in front of her. The people who are audio only are not aware that Janna is as you look like you're posing for a professor photograph right now.
Matt was sharing his life experience that in a bicycle pump, because he's living in his parents' basement, he doesn't own a car, he just has a bicycle. So in his bicycle pump, the valve gets hot.
All I've got is compressed air to keep me happy.
Right, and a spray can, as the air releases, the nozzle feels cold. So the pressure can heat up or cool it depending on which way it's going. So what's happening inside a black hole? Is the person right about it being 0 Kelvin?
No. But they're not right for a very interesting reason. So we know that as the core of a remnant star, what's left after it goes through some very violent throes at the end of its life, continues to collapse and is in fact extremely dense and probably absolutely an unusual, extraordinary, exceptional state of matter. We know that because we see neutron stars, which aren't even black holes. They're a step on the way to black holes. They don't quite make it there. And we know that they're incredibly unusual in terms of their composition. But once it makes it to be the black hole, so it has created a curve in spacetime that is so sharp that we know not even light can escape. That's what we mean by the event horizon. And you might think, therefore, the event horizon of the black hole is full of dense stuff, but it's not actually, because the star can no more sit there than it can expand outward at the speed of light. You can almost think of spacetime as like a waterfall raining into the black hole, and it would have to swim against the waterfall just to stay at the event horizon. And it can't do this, so it just continues to get dragged in with the waterfall of spacetime. And, you know, this is the great mystery. What happens to the star? We don't know, but it's gone. The star is gone. So black holes are cold because they're empty. So if I go up to the event horizon of a black hole, nothing's there. There's no dense object. There's nothing solid. It's empty space. So I like to say, you know, and I've said this, I'm sure, on your show before, black holes are more like a place than they are a thing. They're like a place in the universe, but there's really no matter left.
But you can measure the gravity that it has, right? So something's got to be there.
Yeah, that's right. It has gravitational energy in the curvature of the space-time. There is energy in the curvature of the space-time. That is a gravitational energy. So, you know, it's often really hard to define gravitational energies, but in the case of a black hole, I can actually have a well-defined mathematical prescription for measuring its gravitational energy, and it happens to equal, not surprisingly, the mass of whatever fell into it. Whoa. So it's as though the matter like throws its heft into the gravitational imprint, but the stuff is gone. Now there's another question you could ask about temperature, which is about the Hawking radiation. So at the event horizon, we do think that through this very subtle quantum process, black holes do have a temperature actually, and they are radiating actually, but the bigger the black hole, the colder they are. And the smaller they are, the hotter they are. So they're very cold. They live their lives absorbing things, not emitting. But at the end, you know, in very, very far, far, far future of the universe, those black holes will eventually evaporate away, and the final stages will be explosive.
Yeah, in fact, if I remember correctly, the original paper that described this phenomenon by Hawking explained these as that they would be bursts of high energy gamma radiation, because they at that last moment it would be at its hottest, and very hot things emit gamma rays, and so it's interesting.
So, you know, if you are foolish enough to try to make a black hole in the laboratory, it will explode on you, because the smaller they are, the more unstable they are. And you can kind of figure out, like, how big would it be if it was like kind of a stick of dynamite versus what you're describing, gamma rays or nuclear weapon grade. And you're kind of ill-advised to make a small black hole.
But if you do, you should start with a bigger one just for safety.
Well, then you're going to fall in. So you got to, it's a real. So
what a trade-off that is. Oh, and Earth, it could suck in the Earth. So yeah, that would ruin your day. Yeah.
That would ruin a lot of days, people's days.
So Janna, we can't call a black hole an area of nothing if it contains the severe curvature of the space-time continuum, because that is something. Is that a fair statement?
Yeah, I guess, right, that's fair. We can say, what do we
Matt,
really
notice
mean
how
by
she didn't say it
nothing?
was right. She just said it was fair, right? Okay.
You're absolutely right. Space-time is something, and space-time has energy, and space-time moves, and it's a thing. And in that sense, it's a thing. But it's also, by definition, space, which is a place. I'll take that they very much act like things. Black holes move around, they orbit, they can fall together, they can collide, But when we talk about the size of a black hole, we're talking about a shadow. That's all we're talking about. We're talking about a shadow, like the shadow of a tree, and there's nothing there. No matter. There's no matter there.
While we're talking about matter, so listener Gonzalo Castilla from Mexico asks, and Gonzalo mentions black matter. I'd imagine this is what we would also call dark matter, unless
probably.
there are two different things.
No.
Yeah.
Right.
So I'll say dark matter for this. I'd imagine that's a language thing. But if dark matter can interact gravitationally with normal matter, it is attracted and eaten by a black hole, just like normal matter, right? What happens with the dark matter as the black hole evaporates? Could there be a dark matter version of Hawking radiation, or it only radiates normal matter and a black hole has some sort of mechanism that transforms this dark matter into normal matter?
Absolutely. The black hole will figure out how to radiate all of the information that went into it, if this works. So that includes dark matter information, so that the fact that it was dark would come out in principle. Everything comes out.
Okay, so the Hawking radiation, that calculation does not discriminate between ordinary matter or dark matter or any other kind of matter.
No, it can be electrons and positrons. It can be light coming out in the Hawking radiation. It can be dark matter pairs of dark matter particles.
And that assumes, so everything you said assumes that dark matter is actually comprised of matter and not some other mystical substance.
Right.
Okay.
And there are people who think that black holes themselves might be enough to explain the missing mass in the dark matter. So that's not a particle answer at all. Yeah.
Okay, Matt, keep them coming. See how many we can get in before.
So there's a couple of faster than light questions. So Dylan asks, I've heard a lot about wormholes on this show and have a question. How would we open up a wormhole? I know as of right now they're impossible, but hypothetically speaking, what steps are taken? How much energy would it take? And could we just use a black hole? How do we cut space-time?
Janna, we're waiting for this, and why aren't you giving us the wormhole? We're so disappointed.
I know. I'm busy. I'm going to do it in the future and then come back.
Oh,
I'm going to do it later.
Good answer. Matt, that reminds me during the Science March, which is sad that in the United States we needed a march to defend science. Back several years ago, one of the placards said, what do we want? Time machine. When do we want it? It doesn't matter.
That's perfect. I think MIT once scheduled a time traveler conference for the previous year. So they were like, let's meet in 2019 and have a time traveler conference. Nobody showed up.
Nope. Yeah, time travelers didn't show up. Yeah. Mm-hmm.
I can tell you this about the wormhole. We absolutely, on paper, know how to make a wormhole. So basically, what you do is you write down the shape of the space-time you want, namely a wormhole shape, and then you force matter and energy to create it. And you ask then, well, what does the distribution of matter and energy have to be to create this shape? So you can go backwards and deduce what kind of matter and energy would be required. The problem is it requires negative energies, and that's not something we see in our ordinary experience. Everything has positive energies. Negative energies are super weird. Some people think that they're forbidden in nature. The one circumstance in which you can get negative energies is in some strange quantum situations. I've actually wondered about this. Could we create where you have like finite spaces made out of metals, and the quantum oscillations or the quantum vibrations create a certain negative energy between like these strange geometric configurations?
So you need the negative energy to pry open a hole that would otherwise on its own want to collapse and just make a black hole, I guess.
Yeah, it just wants to keep pinching closed.
So that sounds really dangerous to enter one of these, because suppose you're in one and then it collapses on you. That's a bad day.
That would be
right there. Just saying.
Yeah.
Okay, so we're nowhere near this now, even though you can make it happen on paper.
Yeah, I mean, people at Kip Thorne, they were writing down wormhole solutions decades ago, and they just looked around and said, well, we don't see any matter like that in the universe. So we got to go back to the drawing board and think of a new way.
Right. Okay, so just because something is mathematically possible doesn't mean the universe is going to cooperate.
Right.
That's really what comes down to.
There's other time machines that we know we can make. We can take two cosmic strings, which are literally strings of energy, tension in energy density, and cross them in a very funny way that creates a kind of cut in space-time that allows you to do a little time travel jig. But the problem is they have to be infinitely long and take an infinite amount of energy. So there's never anything that seems compatible with the universe that we live in. And even Kurt Gödel who was friends with Einstein, used to walk to the Institute for Advanced Study with him in the mornings to talk. And he was inspired by Einstein's work. And he wrote down a description of a hypothetical universe that was rotating, not our universe. And he showed that you could travel in time in this peculiar space he invented. And Einstein didn't dispute it. It was correct mathematically, but we just don't live in those kinds of
Okay, so just to admit it, Janna, all we really need is 1.21 gigawatts of energy, okay? That's really all we need. Just admit
I believe it's pronounced gigawatts.
Oh, excuse me. Jen, I think we got to call it quits there. We ran out of time.
Shame. It's always so fun.
Man, okay. So Matt, with your permission, and with I don't want to call it the Stoner Edition unless we have total buy-in from the three of us. Can we call it that?
I'm fine calling it the Stoner Edition, but anybody who knows me knows if I'm stoned, I'm asleep. It's synonymous.
There you
Stoning equals sleeping.
And anyone who knows me knows I have a green card, and
That's right. Northern Europeans have green cards too.
I have a green card, which means I can't get the other kind of green card. But
so we're good here. So Janet, thanks for coming back to Star Talk. It's always good to have you. Good luck with and it's not luck, it's your talent that helps make Pioneer Works what it has been and what it will continue to grow to become. So
thank you so
keep
much.
That going there. And Matt and I are still waiting for our invitation to be something other than in your audience.
Now I can't wait. Are you going to get an invitation?
You got it. All right, Matt, always good to have you, dude.
Lovely to be here. Thank you for having me.
This has been Star Talk, Cosmic Queries, Black Holes, Space-Time Continuum, which we dubbed the Stoner Edition. I'm Neil deGrasse Tyson, your personal astrophysicist.